Hello people and welcome back to another video. In this video, we'll be picking up where we left in our last lecture. We'll be starting off with standard normal distribution. In our last session, we discussed about normal distribution. Today, we'll learn about standard normal distribution, how it is similar and nuancedly different from normal distribution. What are some of the properties of a standard normal distribution curve? And fundamentally, what is the utility of standardization? Why do we need to standardize normal curve in the first place? So we'll begin this discussion by understanding what the basic concept of standardization is. In our last session, we understood what a bell curve or a normal curve is. This right here is the mean. And this right here, as we discussed, is the spread of the curve. We also learned about the 68, 95, 99.7 rule, where we learned that 68% of the data lies in the range of one standard deviation from the mean, 95% in two standard deviations, and 99.7% of the data lies in three standard deviations from the mean. So the concept of standardization is basically shifting our normal curve from its original mean and standard deviation to a standard normal curve where the mean of the distribution is 0 and the standard deviation is 1. Let me elaborate on this point a little bit more. Let's just say this is my axis, this is 0, this is mu, and this is what my normal distribution curve is. So the core idea of standardization is to shift this curve to here. Sorry, I have to draw it exactly the same because the idea is to keep the property of that normal curve intact, the shape, spread, and size of the curve intact, but shifting it to mean 0 and standard deviation 1. So, from a definitional standpoint, how would you define a standard normal curve? It's a normal curve with mean 0 and standard deviation 1. That is the first basic idea. So your mean is 0 and your standard deviation is 1. Now, this is a typical example of a graphical transformation. You have graph A with certain foundational properties. In this case, because a normal curve is driven by mean and standard deviation, we'll say a normal curve with a certain mean and standard deviation, and we are shifting this curve to mean 0 and standard deviation 1. So what happens to all the other points which are in the curve? How do those points get transformed into this new curve? So if this point here, let's just call this point x1, how will I represent? It's not the same point. Let me remove this. It's right here. If this is my x1 dash, how will I calculate x1 dash from x1? Because now the graph has shifted to mean 0 and standard deviation 1. So all the other points have to shift as well. So for a general point x1 on my initial curve, how do I calculate x1 dash, which is a point on my new standardized normal curve? So this is where we come to the z value of a point on the normal curve. So z value or the transformation value is given by x minus mu divided by sigma. This is how all the points on the initial curve are going to be transformed to the new curve. So for a general point x1 bar will be given by x1 minus mu divided by sigma. So this is the general idea of standardization, standard normal curve, and how standardization is done for all the points given in a normally distributed curve. Now, coming to a very fundamental utility of standardization, let me remove this. Now, let us say that there is a situation where I need to study two normally distributed curves, A1 and A2. Okay, A1 has, let us say, a mu of mu1 or a mean of mu1, standard deviation sigma 1. A2 has a mean of mu2 and standard deviation sigma 2. Both of them are both of them have different means and different standard deviations. Now, if I want to study them and I want to derive fundamental differences between these two normal curves, if I go to if I go down the normal route and try to speculate or calculate everything from this instance, it will take me significantly more time. Once I standardize both these curves, what will happen is that since after standardization, both of these curves will have the same mean and the same standard deviation, it will be much easier for me to study the properties of these two normal curves. Now, this is my standardized A1. I'll call this A1 dash, and this is standardized A2 dash. After I standardize both of them, their properties won't change. However, we have transformed them to the standard normal curves, which is A1 dash and A2 dash. Now it is much easier to study their properties. This is one utility. Secondly, when it comes to the area under the curve or the proportion of points, that remains unchanged and unfettered. Because although we have shifted the normal curve, the area under the curve or the area basically the area under the curve is not changing. We haven't changed the fundamental property of that curve. We have just transformed that curve to a new axis or to a new mean. But the fundamental area property of the curve and the proportion of points within a certain region, they remain intact. So please remember these two very important points about the ease of distinction between two normal curves once we standardize them. And secondly, the proportion of points in a given region, those remain unfettered even after standardization or standardized transformation. Now, because when I was explaining you an example in the previous session, we took this example where we had to calculate the area or the percentage of points or the proportion of points beyond a certain given point. Here also, the fundamental properties will be very similar. So again, the complete area will be 100%. In standard normal curve, we have area under the curve as 1. The complete area is 1. You all know mean is 0, standard deviation is 1. So if I have to apply my 68, 95, and 99.7 rule for a standard normal distributed curve, I'll say that 68% of data lies within -1 to 1. 95%, let me do that once again. 95% lies between -2 to 2. 99.7% lies between -3 to 3. This is my 68, 95, 99.7 rule for my standard normally distributed curve, which can be very easily surmised if we have learned the normal distribution. Now we look at some of the properties of a standard normal distributed curve, which are extremely important from an area under the curve perspective. So let us suppose I have a point over here, which I'll call A. There will be another point over here, which is -A. So a fundamental property in both normal distribution and standard normal distribution is that the area towards right of this will be same as the area beyond the left side of -A. So all in all, what we're trying to say is that the percentage of points Z is greater than A. Sorry, let me rewrite this. This proportion will be same as Z less than -A. This is an important property. We'll often come back to this property once we'll start programming in R, and we'll start understanding how do we solve problems which are on standard normal distribution. That is where this property will be extremely handy. Also, a small nuance point here is that there is no such thing as an area on the point. So writing this is same as writing this. So in case of normal distribution and standard normal distribution, the point itself doesn't contribute to the area. And there is no such thing as an area on the point. An area is in a specific region. So writing proportion of Z greater than A is same as writing proportion of points which are greater than Z equal to A. It's like it's one of the same thing. Now, finally, we have understood these properties. Now we'll look at one example over here. It says, let's assume that the birth weight of newborns are normally distributed with a mean of 3,500 with a standard deviation of 500. What proportion of infants weigh less than 2,800? Okay, so first things first, we have to do it using standard normal distribution. You can also do it using normal distribution because that is something that we have already understood. I'll not do it using normal distribution, but I will request all of you all if you can pause this video and if you can solve this problem or at least try and get a basic understanding of this problem using normal distribution, it will be great. I believe this problem is not directly solvable unless I get into the programming aspect of it. And I'll tell you why, but at least you can try and estimate what can be the answer. You won't get to the exact answer, but you can at least try and estimate what could be the answer. But I'll do that using standard normal distribution. So again, I am just brushing up the fundamental concept. If my mu here is 3500, standard deviation being 500, we need to find what proportion of infants weigh less than 2800. 2800 will be somewhere over here. So changing my marker, this area is something that we need to find. Okay. Now I'm shifting this curve from normal distribution to standard normal distribution. For that, I need to calculate the Z value for X equal to 2800. So we have 2800. Upon we have standard deviation of 500. So 2800 minus 3500 is, you'll get minus 700. And you divide that by 500, you will get minus 1.4. So the Z value is coming out to be minus 1.4. I will just erase this upper part. Now in a standard normal curve scenario, this is my 0 point and minus 1.4 will be somewhere here. Okay. So this is the area which we need to find, because what proportion of infants lay or weigh less than 2800. So if minus 1.4 is here, this particular area right here is 50%, which is beyond zero. Change my marker to red. Minus 1 will be somewhere here. This area is 34%. Fifty minus 34 is 16. So this area right here, which includes this and this is 16%. So one thing that we can decipher over here is that the area that we're looking for, which is painted in yellow, that is less than 16%. That is one thing we can say over here. But how do you exactly find the proportion? We know it is less than 16%, but we need the exact answer. That, my friends, we'll be discussing in the next video. I would highly urge you all to watch normal distribution and this lecture on standard normal distribution to make sure that your concepts are extremely lucidly clear before we begin to programming in R and trying to understand how do we find the exact proportion. Thank you so much for watching. I'll see all of you all in the next video.